Okay, so first to start off, let's talk about. So basically, again, there are two parts, right? The first part is the Linux part or C part. The second part is the x86 part. But if you go to the first part, 5A, um, hopefully you have read through it. You found x86 are involved in the first part. It looks like, well, why does the first part also involves x86? That's because you don't need to write code in x86 for this part, but you will definitely need the file images or like the file system, the inodes or other data structures that are used in x86. So basically, this part is you should finish this part using Linux C. I mean, like you write your own C code to finish this part, but these part are like 80% based on the x86. So basically, I'm not sure if Gerard has mentioned the file system checkers, but I think the idea is very simple. I think you've gone through the file system implementations, like the very simple file system implementations in last lecture, and the checker is like to protect your file system from like corruptions due to like power outage, something like that, to restore the informations or the files before this crash, before the file system, this operating system crashes. This checker is very simple. It's just you just read in this file system image and then do a bunch of list of sanity checks, mostly focused on like the inodes, like the files and directories and data blocks, all to make sure all these make sense. Also the bitmap, and then you go through like instruction by instruction, and after you and you should throw the errors or exceptions accordingly. And after you go through this list, you are done with the checker. And if none of these happen, which means this is a good file system image, and which means it's not corrupted. So this is what you do in like a conceptual level. And to understand the details, we have to go through the file system images of x86. So we have gone through in the lecture, we have gone through the file system implementations, right? You have some ideas of what the inodes are, what is the data block, and how they are related. But I think in x86, there are still some differences and some minor differences and also some details you have to focus on. So here to help you guys better understand the structures, I have had some slides here. So if you go through the file system layout in x86, I don't want to go full screen because I have to switch from the slides to the terminal from time to time. So I'll go this way. So basically, oops, sorry. So in the file system image of x86, they are basically divided into multiple blocks. And each block in xv6 is 512 bytes. This is kind of a hard-coded number. It's defined in the macro of x86, so I think you should be very familiar with this number after you go through this whole part. So each block is 512 bytes, and for the very first block, it's unused. And the second block is the super block, right? This is the idea mentioned in the lecture. I think I'm not sure. I think in terms of different file systems or operating systems, probably the very first block is the super block. But for x86, the first block is unused. Okay, and then followed by a bunch of blocks that store the inodes. Okay, and how many blocks will inodes take? That depends on A, the size of the inode, right? Each inode. B, how many inodes there are. We'll talk about that later, but like this is like a chunk of blocks reserved for the inodes information. And then the next block is also, again, is unused. This is like specific to x86 and specific to this project. So you will definitely follow this layout, okay? And then we come to the bitmap. And for bitmap here, I think there are multiple bitmaps in normal operating systems, like inode bitmap or data block bitmap. But for here, the bitmap represents the block bitmap. If a certain bit is 1, then it indicates that corresponding block or data block that 512 bytes are used. Okay, 0 otherwise. And finally, we come to the data, which are including the file data, right? And also the information of the directories, okay, like different entries of the directories. We'll talk about that later as well. And you can see there are basically 3 important data structures defined in x86. The simplest one is the super block. It's just here, right? The second block. And it's very simple. There are just 3 integers. Size, meaning size of the file system image, the whole image. This is in a unit of blocks. Okay, it's not in unit of bytes. It's in unit of blocks, and then number of blocks, and then number of inodes. Right. This is very simple, and the most challenging or most confusing part are these two guys. Okay, the first one is the inode data structure. So it looks very simple, right? There are like 4 short types. I think the major, you don't need to care too much about major or minor. All you need to care about for this project is the type, which is the file type. I think they are all defined as a macro in x86. As far as I could remember, if type is 0, it means this inode is not used. Okay, if it's 1, it means it's a directory. If it's 2, then it means it's a regular file. And I think there is a number for 3, but we don't use it here. But I think we can grab the code in x86 to take a look. So like. So I think it's defined. You can search for dynode. Okay, it's defined here. So it's in include fs.h. Right, this is a super block. This is the inode data structure. Okay, here these macros are some. You can treat this as a magic numbers, but I'll talk about it later. But for now, it's just for the convenience of the calculations. Okay, let's finish this inode data structure first. Okay, so again, you don't need to care too much about major or minor. You only need to care about the type. And also nlink is number of links to inode in file system. Okay, so here in x86, as per current version, only hard links are implemented. Okay, so when we say links in x86, we are talking about hard links. Soft links are not implemented in x86. So potentially it can be another like sub part of this project, but for the simplicity, we don't let you guys implement soft links. So okay, so yeah, I think it used to be another subpart of the project. Right? So the links are just the hard links, and the size is size of the file in bytes. And here is a very important array, which stores the data block addresses. So what does it mean here? So I probably later show you the diagram. You will be more clear. But but right now, this address is conceptually just stores a bunch of integers. Each integer represents the block number, so that you can infer to that, go to that address to fetch the data stored there, basically. Okay, remember, inode can represent not only regular file, but also directories, right? That's why we have a type here, right, to indicate whether it's a regular file or it's a directory. So if it can be slightly different in terms of either it's a regular file type or a directory file. And the address here will be also different correspondingly. I'll also talk about later. The third data structure is called dirend. It's particularly related to the directories. So I think it's short for directory entry. So it's simple. It only contains two fields. The first one is inum. This inum is just the inode number. Okay. So I think in normal, like in Linux, the root inode has got a inode number of 2, right? But I think for x86, the root directory inode is 1, if I remember correctly. But so this is just the inode number of that directory, and then it's the name, which means it's a string basically. It stores the basically the directory name. Okay, so the data structure looks very straightforward, right? It's just nothing fancy, but it can be very confusing. So let's go to take a look at the visualized version of these data structures. Oh, before we go to here, let's answer the questions I asked just now. So how many inodes should we put here? Again, depends on two factors, right? One is the number of inodes in this file system. Second is the inode size. Each inode, how many bytes does it take? So according to this data structure, can you calculate or can you estimate how many bytes does one inode take? So basically, I'm asking you what is size of the inode?
Is it short?
Right, short.
2.
Yeah, exactly. Short data types only take 2 bytes. So 2 times 4 is 8 bytes. Int, it takes 4 bytes, so it's 12. And okay, so what is this macro? So yeah, you can again go to ndirect, right? This is 12. So what does 12 mean here? It means each inode takes 12 directory addresses, and the last one is the indirect address. If you can remember the file system implementation for large files, right? If the file is very large and it does only 12 or n direct blocks cannot hold all the files. All the data in the file. Then we create an external block where it stores an extra second, like the indirect pointer pointing to more data, right? This is what this extra one data block represents. So in x86, we say we have like 12 direct blocks to directly store the data for a file or directory, and later we have one indirect block to store a bunch of pointers that points to more data. Okay, so here it's 12. So 12, that's 13 times 4, that's 52, right? 52 plus 12, 64, right? It's a good number. So size of inode is 64. It's kind of carefully calculated such that it's it's also can be divided by the block size, which is the 512, right? So you can calculate each block contains how many inodes. That is 512 divided by 64, right? Which is 8. So each block can store 8 inodes in XV6. And I think normally the default number of inodes in XV6 is 200. So there are 200 inodes in XV6 by default. So altogether we will need, so each block, I think it's shutting down again. Okay, so each block can store 8 inodes, and we have 200 in total. So how many blocks do we need? 25, right? So yeah, so we basically need 25 blocks to store all the inodes. Okay, but try not hard code like 25 or 8 or whatever in your checkers, right? I don't think this is a good way. Try to be as flexible as possible. Try to be as generic as possible. So that's why we need the help of, need to show the code in XV6, a bunch of macro to define the calculations. It's not hard coded. Okay. While we're waiting, any questions so far?
Can you just repeat that last part and follow the math?
Okay, so I can write it down. Like,
I understood that each block can start 8 inodes, but I didn't understand where the 25 is coming from.
yeah, because we have like 200 inodes in total.
And where is that defined?
This is defined in the
Struct superblock and inodes.
right.
It's just hard coded. We're gonna have 200.
Or the superblock is
This number is you can exactly you can use like SB, which stands for this super block. It's got 3 fields. One of the fields is n inodes. So this is 200. Okay, let's turn it on. But I mean, try not to hard code, but still there are some primitive numbers that should be hard coded. One being the block size, 512. This one is hard coded. I mean, by saying hard coded, I mean it's already defined in a macro in XV6. So you can potentially change it, right? But I mean, yeah, try to be as generic as possible. Send to screen. Okay, so here, look at this line, inodes per block. So this macro IPB, inodes per block, is calculated as B size, which is the block size, 512, divided by size of inode, which is 64. So that's 8, right? 8 inodes per block. So you can just use this macro instead of 8. That's what I mean, not hard code 8 here. Okay, and like here, block containing inode I. This is actually a very good method or way to locate which block does a certain inode reside. Does that make sense? So like the 2 here is actually because of these 2 guys, right? the unused block and the super block, because the very first inode starts at the third block indexed 2. We start indexing from 0 to 0, 1, 2, indexed 2. So that's why we need to add 2 here. And you do this integer division, you'll get exactly the location of, like, if an inode has a number of 14, for instance, then 14 divided by 8, right? It's 1, right? And 1 plus 2 is 3, which means it's at the fourth block, which is block index 3. Okay, though it's a very convenient way to locate where the inode is. And here is the bitmap, because so bitmap I'll also talk in details later. But like bitmap is so 1 byte is composed of 8 bits, right? So each byte can represent 8 blocks. So that's why we times 8 here. So if the bitmap takes the whole block, then at most this many blocks it can be mapped, right? Because each bit is associated with 1 block. So and each byte corresponds to 8 blocks. And 1 block size of a bitmap can map with this many blocks. So there are a lot of math here, so you have to be very careful not mess up with the math. And here is some more like sophisticated calculations, but like I think the comment is very straightforward, just to calculate block containing bit for block B. Okay, I'll just leave it here for you to understand. Okay, here is another macro, which is the directory size, which is here. Why is 14? The reason is that, so say suppose it's 14, right? Then each char is 1 byte. So this field takes 14 bytes. And short takes 2 bytes. So the reason it's 14 is because it's just set in such a way that guarantees that the size of struct direct or directory entry is 16, which can be also divided by the block size. So, okay, after figuring out this math, let's go to the visualization. Okay. So I think it's very helpful, at least to me, to understand the layout or the data structures of the inodes. So as I said, inode can be both used by a regular file or a directory. So let's go to the regular file representation of the inode first. So again, the size of the inode is 64, right? 64 bytes and contains multiple fields. This is corresponding to this, right? And these are just the regular like short type. Okay, starting from here, there are like 12 addresses or 12 integers. These integers represent the block number, okay? And each of them points to a block of data. Excuse me, right? Each data takes 1 block, which is 512 bytes. Okay, and the tricky part is the last address, which is the 13th address, which is the indirect pointer. It does not directly point to a data. Instead, it points to a block in which more addresses are stored. So that's why it's the indirect or like second order pointer, right? Okay, so how many addresses can this block have?
128.
Right, I already have the number here. Why 128? Because
12 bytes divided by
right, exactly. You can do the math again. So basically, one block is 512 bytes divided by size of address, which is size of int. Size of int is 4. So we can have 128 more addresses in this block, okay? And each of these addresses point to new another further data block, right? Okay, this is basically the layout of inode as a regular file. And here's a very natural question, right? You can ask. So what's the maximum possible size of a regular file can in x86? You don't need to give me the exact number. You can just do the give me the arithmetic formula equation. So basically, it's 12 times 512, right? Plus 128 times 512. So basically, it's 128 plus 12. It's 114, right? 114 times 512 bytes. So that's the maximum size for a regular file in x86. Okay.
And x86 only ever does one level of direction.
Right. We don't have further pointers, no. So x86 is very simple. And you calculate that, I think it's very small size. This is a byte, not even KB, right? It's so like it's 70K. This is half K, right? And 114 is 140, so it's only 70 KB. That's the maximum file size. So that's ridiculously small, but like this is a very simple system. So
The project is optimizing for small files,
right,
smaller than 70 KB.
right. Yeah, we'll talk about later, but like yeah. Okay, this is the like a regular file representation. What about directory? How does directory look like in x86? So again, we use the inode. The only difference is the type. Right now it's 1, and again it's 64 bytes. And again, we have 12 addresses. But now, each of these 12 addresses are not pointing to the data. Instead, it points to a bunch of direct data structure. So what does direct store? So again, it's short for directory entry. So each directory you can have like subdirectory, right? Or you can have files. So the files and subdirectories in this directory are stored here, the information. And you can remember the size of direct is 16, right? Size of direct is 16. 2 plus 14 is 16. So 512 divided by 16 is 32. So basically, each block can store 32 directs, meaning each block can store like 32 files and subdirectories, and we have 12 this many. Okay. And again, we have the last address is the indirect pointer, pointing to another 128 addresses, where each address will point to more directs. Okay, again, you can calculate how many files and subdirectories can a directory have at most in x86, which is again 12 plus 128, which is 140, times 32 files or directories. Okay, so that's the layout of the directory. So when you do the especially part A, I think you will frequently go through this too, guys, and alternatively, basically. So I think this is very helpful, at least for me. You can easily get confused without this visualization, I promise. So definitely, I would just upload it. Yeah, it's very helpful. Okay, so does that make sense? Any questions? Okay. Yeah, okay, this is another minor part, but also important. This is also corresponding to part A, the bitmap. So each bit in the bitmap is associated with a block, not the inode. I mentioned that before, right? So this is essentially the block bitmap. Yeah, although the very first block is unused, it is always marked as 1 in the first bit of the bitmap. And so are the blocks where the inodes and bitmap itself reside. Okay, and bitmap is grouped by byte, right? And because x86 is using the Intel x86 processors, so these guys use a little endian. So if you can still remember all the way back at the very first worksheet, you worked with like endian is. Probably back then you don't understand very well, but I think right now you should have a better understanding of what endianness means, or like little endian versus big endian. And I can give you an example to better understand this. So like this is in hex, right? So in hex, 2 hex digit represents 1 byte, right? And if you translate it into binary, you have like 8 bits, right? This is what each bit means. So bitmap, so each bit is either 1 or 0. If it's 1, its corresponding block is used. Otherwise, it's 0. But what does a little endian means? It means we read the bit in reverse order, but grouped by byte. So first we divide these into bytes. So we divide into 2 groups, FF and C2, which is 11111. This is one group, and this is the second group. And then we do the reversal order traversal, basically. We start from the rightmost digit, or the least significant digit, which is here. We index this 1 to be 0, 1, 2, 3, 4, 5, 6, 7. Okay, this is the first byte. We finished. And for the second byte, again, we start from the right, which is 8, 9, 10, 11, 12, 13, 14, 15. So by saying little endian, we say we start from the right, or the least significant digit, group or byte by byte. Okay, but for big endian, I think it's more or easier to understand or less confusing. We start from the left, which is, I think it's very straightforward, 0, 1, 2, 3, 4, 5, 6, etc. But for little endian, we start from the right. But we should first group it in byte and then do that from the right. Okay, so this is what the bitmap represents in terms of the little endianness.
This is all the blocks where the inodes and bitmap reside, so they're always marked as 1, even if they're not all bitmap. So the bitmap for like, so you said you had.
So I mean for the very first block and for this block, although they are unused, they're never used. So in bitmap, it's always 1.
And the bitmap is 1. But then we have 25
inodes.
inode blocks. Are those always marked as 1?
Right.
Even if they're not actually.
Right. Exactly. So the only scenario where we will reset the bitmap or set the bitmap to 0 is when the data is removed or like is cleared. That specific, for instance, we remove a file and its associated block data is we don't actually clear that chunk of data. We just set its corresponding block bitmap to be 0. That's what bitmap is used for, right?
So really we can just ignore the bitmap values for everything other than the data blocks? That's the only...
Basically, yeah.
Because it'll just be 1.
Yeah.
Should we check if they're
Well, I think you can safely just start from here. Yeah. Okay, so this is the bitmap. Okay, now let's come to some demos. Let's take a look at what the x86 image look like. Okay. I think I'll go to. So, let's see. Okay, let's take a look at this image. Oh, I think that I missed a very important part for the part A is that how the image was made, right? So actually, there's a code in x86. If you go to x86, there's a so you are very familiar with kernel, include a user of even fs, and there's a last directory which is called tools. Probably you never looked at it. And if you go to this tools, you will see there is a executable called makefs. So this executable is compiled from here, this C code. This is in x86, by the way. And this C code is not the user program in x86, nor the kernel like C.C file in x86. This .C file is the authentic Linux C file. Okay, so in this C file, we just use printf and 1 as the first argument, and we don't have C printf, something like that, the weird thing in x86. This makefs.c is completely purely Linux. Okay, it's not x86. So if you take a look at it, oops, sorry. See, when you include, you will have this angular parenthesis instead of the quote, right? In x86 user program or kernel, it's always quote. Yeah, there are a bunch of definitions, like some numbers. Okay, here is actually, you can see very familiar. It's actually just corresponding to the 3 fields of the superblock. Number of blocks, 995. Number of inodes, 200. Size, which is 1K. This is not in bytes, it's in blocks. So there are like 1K blocks in the whole file system image. Okay. And here actually it's just converting the byte to the little endian. If you are interested, you can take a look at it. There are a lot of bit manipulations or bit operations are involved. These are just doing exactly what I said here. Yeah, doing this reverse weird order, but yeah. And here is the main method to create the file system image for x86 called makefs. Yeah, it does a lot of mathematics here. You can see very familiar, right? This is like to locate, I think this is 8, right? Inode per block. So this is number of inodes is 200, so it's 25 plus 3, which is 28. This is the corresponding to the bitmaps, so I think it's 1. So it's 29. So this number, I think it's 29. Why it's 29? You can go to here. 1, 2, plus 25 is 27. 26, 28, 29. Okay. So again, don't try to hard code. I'm just trying to walk through some concrete example. I'm doing the example here. I'm not hard coding. Okay. So I'm saying this line is to locate where the data block is, essentially. And if you are using these parameters, you'll get 29. This is block 29 to store the very first data block. 1, 2, 3, 4,
Block 29
plus 25.
when you're starting the count at 0, because it's 29 are taken up by that. Because there's 4 individual
Right.
blocks and 25 for the inodes.
Right. So there are 29. Oops, there are 29 blocks before the very first data blocks. Okay. Yeah, a lot of math. So sorry about that, but like if you are familiar with the layout, hopefully you'll get used to that. Yeah, this is essentially just writing each block, right? And using the WSECT. I think, I'm not sure if I will go through this, but for curiosity, we can take a look. Yeah, it does a bunch of write system call, right? Each system call writes 512 bytes, which is one block from this buffer. This buffer is passed from here, and I think so. Where is the buff? Yeah, yeah. I think you should. I think. I'm not sure if it's very useful to walk through this, but I think it's definitely useful to walk through this. But like this is a very long code, and what it does essentially just to create the file system image based on the file system here. So you see this, there's a FS folder in x86, right? So here is a bunch of executables and the README. Oh, I created a hello directory here for the demonstration later. But like essentially, when you do run make fs, you are essentially creating a file system image based on the file system here. Okay, so whatever files or directories are here, after you run this make fs, all the data or corresponding information will appear in the image. Okay, so let's take a look at what the image looks like. So it's okay. Sorry. Before doing that, let's just try to make clean. This is a clean one, right? There's no image here, no FS even, no file system here. And if we type make, this is like everyday. And now we have like the FS here, right? And if you go up to this very lengthy or tedious dumps of the compiling, you'll look at, discover something like at here, this line. See what it does? This is exactly what the executable of the makefile reside, right? And this is the file image's name, and this is the file system. So if you can try to do this, copy this line and make clean. Oh, I cannot make clean, because if I make clean, then FS is gone. FS should be here. So I don't make clean. I just remove the fs.image. I just remove this image, okay? And I run this code. You can see the file image is created. So this is essentially what this makefs does. It just creates the file system image from the file system in FS. So you can see we have multiple like executables and README here. And you can, so like I create a make directory called hello, for instance. Okay, now let's remove this fs.image and let's try to recreate the file image based on the fs I added it just now. I created a hello here to see if it's it takes effections. Okay, so you can see here we have a hello here, and if you make qmove ls, you'll see hello is here. Okay, so this is the directory I created just now. Okay, now let's take a look at what the fs.image looks like. What's the like this? Okay, when you use like Vim or Emacs and you got this, it typically indicates that you are looking at the binary file. So so the file image is not a well-written or human-readable text file. No, it's not. It's a binary file. So let's use our old friend called XXD. So actually, there's another trick I learned recently. Is we can do. I think Vim is very powerful. I'm not saying bad things for Emacs, but for this demonstration, I only use Vim. I definitely know there are some alternatives, like a lot of ways to use Emacs, but for sake of demonstrations, I use Vim. Okay, there are a lot of tricks in Vim to decode this the binary file. You can use like the colon, which means to type in some commands, and because the command is called XXD, and the exclamation sign is to indicate it's a bash command, and before that I have to add the percent sign to indicate I want to replace this whole garbage into the binary file or the hex decode I want to see. Okay, now it looks better. So this again, it's an hex representation. So each 4-digit of hex means 2 bytes, right? So you scroll down, looks like still garbages. We can try to search for like readme. Because this is a file image, right? There must be some strings or like human readable letters here. Yeah, there is. So you can see there's a readme and cat, echo. So this looks very familiar, right?
Is the whole thing in Little Endian, or is it just the bitmap that's in Little Endian?
That's a good question. I think the whole thing is in Little Endian. So when you try to interpret an integer, or 4-byte integer, here in you are conforming to the Little Endian. Yes. Okay. Okay. So can you guess which section or which block does this correspond to? According to these the two.
One of these star and
So it shouldn't be file, right? Because they are the file names, right? File names must be associated with a directory. Yeah, so you're correct. We are looking at the one of the inode, which is the directory, right? Directory inode here. And can you guess whose inode, whose directory, which directory is this?
FS. Where'd you put the hello?
Hello is down here. Yeah, it's in FS, but like
Wait, isn't it root because we mapped FS?
exactly, it's root. That's the root directory. So this is the root directory. So this block stores the root inode. Sorry.
So that's the direct.
Yeah, the direct. Mm-hmm. Yeah. So again, the direct data structure has got only 2 parts, right? One is the inode number. The other is the name, the character. So you are seeing the character here. Okay. Okay.
Did we map FS to root? Was that in Make MKFS?
Sorry, say that again.
Where did we map FS to root? What is that?
Oh, we don't have that here. We don't have a makefs.c or makefs executable in this file system because it's in
but
tools.
You said we mapped FS to root, and that's why this was root. Where did we do that?
It was the argument when we called
Right, exactly. Yeah.
Right.
Yeah. Mhm.
So passing in, we said this is the root directory.
And here you can see what's this. This is actually the content of the README. So this is we are reaching the data block of the README file. This is the file. They are all human readable, right? And here are actually also the data of the file, but it's no longer a text file. Instead, it's an executable, which is probably the very first executable, which is the cat. So again, these are the executables, right? It's not the C code. It's the compiled executable binary file. So that's why you'll see this binary file here. And if you scroll up a bit, you'll see a bunch of Fs. What are these? So this is the root, right? Root inode. Scroll up.
Oh, the unused block?
No. So if it's unused, they're 0, right? So I think root is the very first inode, right? So its data should be at the very first block of the data block. So go up.
So it's the bitmap
Right.
for all of the stuff before
Exactly.
the data.
Exactly. This is the bitmap because F is a bunch of ones, right? So you can see all these are ones, even for like the unused and these unused, they're all ones. So you can just start caring about from like the 29th or the number where after the calculation you got 29, and you can locate somewhere here. Yeah, 20, 24, 28, somewhere here. Yeah. Okay. So, let's do more stuff here. Let's make. Oops. Oh, I see. I think I didn't clean. Okay, let's try to create, because I made clean just now, so the hello is gone. So we can create a file here, like hello, like a world, and you can see there's a world here, and we can try to remove something, like we can remove kill, for instance. Okay, kill is gone, world is still here. But if you exit, if you go out of x86, you go to FS, actually you see no changes. You still see kill, and you still didn't see world. So the question is, where does this information or the modifications saved? It's not persistent, actually. It's not persistent on the Linux, but it's persistent on the, exactly, it's persistent on the image. So all the modifications, like you can create a files, right, write or modify whatever in the x86, but after you quit x86, you are in Linux. And these changes are not affected in the real Linux. It's only persistent in the file images. Okay, so to prove that, let's see if we did something to the image. Okay, so again, let's take a look at the image. What? Interesting. Yeah, right. I don't know what I did, but let's see. Okay, let's go back to this. let's search readme. Okay, it's here. Okay. See, so this is gone. It used to be the kill, right? And it's gone because we removed it. And actually, you can see the very first byte is actually corresponding to the first field of direct, which is the I number. And I think here is the dot, meaning the root, and dot dot, meaning the parent. So if you translate this 2E into ASCII code, you'll get a dot. Believe me, okay? Now this is dot dot for the parent, but the root's parent is also the root itself. So they are both of them has the inum of 1. And starting from README, it's got inum of 2. And this is the ASCII code for the README, believe me. Okay. And this is cat, this inode 3. And I think kill originally has got inode 8. But because you removed it, so this entry is reset to 0. And you can see in world, just created inode 14 here. Okay. So.
Sorry, I think I
Mhm.
missed this stuff.
Okay.
So you created those while you made those modifications when you were running that SB6 on the third.
Mhm.
So at what point did that update the image?
Mhm.
Like when did that happen?
So what I did is like make dir and remove. These are the user program in x86, not the Linux, right? And under the hood of this user program, I think we call system calls like write, and write actually modifies the images.
Okay, so this is assuming that there's an fs.image file?
I think.
Would x86 run without it?
I mean, when you do system, so I think we will walk through the write system call later, but like I think for the fast system associated system calls, you will definitely modify the images, essentially. Although I'm not quite clear where exactly it is, but I think it's because you can just attribute it to the system calls of fast system related system calls, write or read. Yeah. Mm-hmm.
I mean, I guess like my question is it like hard coded to look for that specific file? That like that's how it.
So which file you're talking about?
Because it looked like it was all happening in fs.image, but we had to create that manually. So
Oh, you mean when did this guy create it?
right, wasn't that created when you like ran?
So the first time it was created is when we do make.
Oh, in the make file.
Right.
Okay. So because this isn't the other. version.
Because if you scroll up, right here, this is all the compiling information, and you at the last line you have this line.
So this was added into the make file.
Yeah,
So-
makefile has this line. I think you can take a look at the
So
makefile.
like when previously we were using x86, I don't remember there being an FS directory.
So
So- After you do the make command.
Yeah, so it's-
the
it's-
downloaded copy isn't there.
it's encoded in the it's encoded in the makefile. Yeah, yeah, exactly. Yeah.
So you can assume it's there. But
Yeah.
x86
Okay, so let's see what do we have. Okay, so this is some demonstrations for make FS and a closer look at file images with XXD. Okay, I showed you how to inspect FS image, but because in project part A, you will try to have. You can definitely use the images or test cases we provided, but if you want to create your own test case, so in this part it's very special. It's not like previous. The test case is like a C code. for the part A, all the test cases are different images, basically. So because you are writing the image checker, right? So you definitely want to write your own, create your own images with some like you want to corrupt it somewhere so that you can make sure that you implement this checker correctly. So I think the most convenient, most direct way to do that is to directly edit the image here. But since it's a binary file, it's not as easy as, okay, you can try to do this, like you can try to do this, like change 0 to F, and then you can quit. You can go back to C again. I think that's because no, this is not what I want. Let me make clean. Okay, so like fs.image looks different than what I tried to do. For instance, I want to modify this guy here to FFF. Modify exit. Okay. Okay, then I think that's it. Yeah, because I thought there are more complicated ways to do that. I'm gonna show you guys, but I think it works here. So, okay. Okay. Yeah, you can do this way to modify the image and try to, after you finish writing the code, you can run it.
Are we going to modify the image just for testing if we're detecting things correctly, or we would actually modify the image to do the checking?
The previous.
Okay, the testing.
Right,
okay.
The testing.
Makes sense.
Okay, so how to read the image? Sure, you can use the read system call, but I think a more convenient way to do is use mmap. You have already used mmap in like P3A, right? But that's for like to create a shared memory page. But for this project, you again use mmap. You get a pointer, but you don't share it. But I think this mmap is much way convenient than read. The reason is that if you do read, so every time you call a system call read, the buff. So how to say that? So like you have 1 KB's file, right? You read it, and the first time you read to read the first 10 bytes, for instance, and the second time you call read, you are not starting over. You are continuing, right? Start from the 11th byte. That's not very convenient. But in mmap, it will return a pointer to you. And then you can do whatever you want with that pointer. You can do any pointer arithmetics, and you can cast that pointer to like int or char or any of these data structures, right? So that you can better manipulate it. So I would definitely suggest you guys use mmap to get access to the image. And here's a demo to, yeah, I think it's a pretty long, but yeah, okay, I think I'm almost done with this. So to save us time, I've already written several things here. I don't want to show you guys line by line. I mean, start from scratch because it takes a while. And I'll just explain to you. I think it's most of these guys are very straightforward. So the first line is just open the image, right? Definitely. You return a file, the file descriptor. And then I want to get the size of this image. And I think you have used this system called fstat before, right? To get the size of the image or the file. And then you call mmap. Most of the arguments are the same with what you used in P3A, except for this tag, which is now map private. Previously, you were using map share, right? Because you are sharing, but now we don't share, so you can just replace it with map private. And other than that, I think it's almost the same. For the protection bit, you will use read because you only read the image. You don't want to modify the image using this method. Okay, so again, modifying the image is just for the sake of testing. It's not for the programming. Okay, so you will not modify the image in your C program. So that's why you can just use approach read. Yeah, this is the size of the file, the image. And now you get the pointer, which is like a generic pointer, void pointer. Then you should cast it to whatever you want. But if you cast it incorrectly, you will get garbages. That makes sense, right? If it's an integer, you cast it to a char, then you get nothing, or you don't have a sensible semantics. So you have to be very careful which byte or which block corresponds to which structure. So that's why you need to, from time to time, go through this. Okay, so the first thing is because this image pointer is now pointing at here, right, the very first unused block. Because it's unused, I want to directly shift to the second block. So I just shifted by 512 bytes, which is the B size, right? Can do the pointer arithmetic very conveniently. And you can see here, I just did a first I did the pointer arithmetic. I added by 2 blocks. Why do I add by 2 blocks? And such that I'm here, right? So that's why this is like the inode pointer, right? Pointing here. So offset is 2 blocks. And then I cast this void pointer to the dynode struct so that I can manipulate the dip here. Yeah, probably we can skip bitmap for now. We can go to here, the super block. So super block is offset by 1 block, right? So I added only 1 B size. So if I shift it by 1 block, we come here. We are here. And for bitmap, yeah, this is for demonstration's sake, I just hard-coded 28 so that I reached here. And for data, you can just add by 29, but try not to put numbers here. Okay, try to use the calculations in the in Axis6, the header file. Okay, so I will just use GDB to go through this. So the reason why I declare this pointer is I want to take a look at using this pointer to inspect the data structures of basically the inodes. Okay. So I'll just I think I've already compiled it, and GDB checker. I will run. I'll set breakpoint at main, for instance, and I run the image, which is I don't need the argument because I think I hard-coded the image called fs.image in checker, if you could remember. So I don't need the argument here, I can directly run. Okay, now we are in the main. Now we're opening the fs.image. Everything looks fine. And we can print out the buff, which is what we got from the fstat, right? And we can get its size. Yeah, this is many bytes. This is a very large file image. Okay, next. Okay, we've already got the pointer, right? And then we got the inode, the dip. I think I'll just reach the end. Okay, now let's take a look at the SB, which is the super block, right? We got it from here. But this is just a pointer. When we dereference it, you can see this is the 3 fields of the super block, right? Exactly corresponding to what we've seen in the makefs.c. So the 3 fields. And let's take a look at the inodes, which is called dinode, dip. Okay, so this is actually the very first inode, right? When I dereference it, this is essentially equivalent with 0, right? So this is the very first inode. You can see everything is 0. That's because for inode 0, it's basically not used. We start from the root node start from the first one, which is dip 1. You can see. So now its type is 1, which means that its directory and its size is 512, and it's got an address array, and only the first entry is populated, which is 29. So this inode is representing the root. How do we prove that? We can actually go to see this address 29 to see, because we know this is directory, right? Because it's got type 1. Then we can go to the address from here. Okay, directory, address, block 29. In block 29, it stores a bunch of dirends. And in each dirend, we have the name and the inum, right? So that we can prove that it's indeed the root node. So how do we go to block 29? So starts from 29, right? Each block is 512 bytes. So we can do pointer arithmetic. How do we do that? We can go to, we start from the very first pointer, right? And add it by the offset of 29 blocks, which is 512. This is a pointer pointing to the very first byte of the data block, right? And then we dereference it. Okay, we cannot because it's a generic or it's a void pointer, so we cast it to, what do we need to cast? So that's why I said it's very confusing. You have to understand what exactly data type it's holding so that you can cast it correctly. If you try to cast like int, you get garbages. So yeah, someone said it's dirend, but why it's dirend? So it's a directory 29. Okay, now we see the diagram. Okay, it's containing a bunch of dirend. That's why we need to cast to dirend. So that's why I said you have to refer to it very frequently. Okay, because it's defined in struct, it's not struct defined, so we have to have a struct here. Okay, cool. We got the very first dirend stored here. You can see its corresponding inum is 1, which means it's the root. And the name is dot. And what's this? Because the name takes 14 bytes, right? And trailing 12 are zeros. So
it just fills in zeros.
yeah. Okay, what if I want to see the second dirend? So this is a pointer, and I dereferenced it, I got dirend. If you are more accustomed, you are more familiar with the bracket, you can do like this, right? This is because I have to you have to do this first and then bracket. This is the very first dirend. This is the second dirend. You can see this is the parent, right? and the third one. Because I was using different the image. So in that image, I have this third one. It's not README. I didn't use the XV6 image, but that doesn't matter. It's just some other directories or files in the root, under the root, right? You can go forever. I think there are a lot. I think there is another convenient way to list, because right now we are only looking at it one by one. You can list it by starting from 0 and do the @ sign. This is completely GDB features, okay? Like from 0 to all the way to 10 dirents. This is a list of the dirents we have. I think we ended here. The reason is that for this dirent, its inum is 0, which means it's not existing. It's not used. So we just end it here. So there are, the first is the dot, which is the root itself. The second is the parent, which is still the root because the root's parent is also root. The third is the directory, and directory 2, file 1, whatever. And these are just the I numbers corresponding to each of these files or directories. Okay, so this is so using pointer arithmetic, you can, if you properly cast it to the correct data type or data structure, you can get the information here. Otherwise, you'll get garbages. So that's why I highly suggest you guys get very familiar with this layout, and also familiar with pointer arithmetic, so that you will correctly parse basically or get useful information from the images. Okay. So this is the inode. Let's take a look at a direct. Yeah, this is a directory, right? Because root is a directory. Let's take a look at inum5, for instance. One more example. So for inum5, we use this. We use this, right? Because dip is the pointer pointing to the inodes. So 5, the index is corresponding to the inode. So this is the inode of dir2. Okay, and you can see dir2 has got a bunch of addresses at 32, and then you will go to 32 by the offset of 32. And you can see there are only 3 files. First is dot, which is itself. The second is dot, the parent. And the parent, dir2's parent is the root, right? And you can see the inum is 1, which is the root. And the third one is the file 3. It's the file 3 is in dir2, right? And the rest are empty.
So really dir2, that was item 5.
Yep. Inum5 is dir2. Yeah, it's kind of, you have to read this way. 6 is the inum of file 3. Okay. Does that make sense? I know it's very confusing, but okay, let's take a look at a file. Let's look at this file. This file is very large. This is a max file. It's at inum 9, right? So let's go to dip 9. Okay, look at it. So it's got a size of this many. So you can do the calculation here. Divided by block size. This is very familiar, 140. So this is exactly the largest file in XV6. Right? 128 plus 12, 140. Okay, so yeah, this is a very particular test I made. So basically, I have this. This is that's why it's called a max file. Right? It's a max file in x86. So it's this many, 71 kilobytes, and okay. And if you go to the addresses, you can see it populates every entries in the addresses, which is corresponding to these 13 entries, right? The first 12 are pointing to the data, and the last one is pointing to the indirect. So which means from 35 to 46, they are like just stores the regular data. You can take a look. How do we go to like block 44? Using this, right? Like 44. And what I want to look at like the first 10 bytes. And now we will not cast it to direct because it's no longer holding a direct. Instead, it's just holding a bunch of chars, right? If it's a regular file, it's a text file, it's a char. But if it's a binary file, then there's no way to see meaningful things. But yeah, thankfully this max file is a regular text file, so we can cast it to char. And see it's a bunch of A's because in this file it's just a bunch of A's. You can see all the way to 512, which is 1 byte. So A repeats 512 times. Okay, and you can go to like 46, for instance. Still, they are all A's, which is stores the data here. And the only special case is the indirect entry, right? And now it no longer stores the data, but instead it stores a bunch of addresses. So where is it at? It's at block 47, right? If you try to cast it to char, oh, garbages. Why? Because it does not contain chars, right? It contains integers because it stores addresses. So you have to cast it to int. And it's no longer 512, right? It should be 128. Right, only 128. And you can see, look, everything makes sense. So these are more addresses, like the indirect addresses to store more data. Right. So start from 48 all the way down to 175. And you can see, like, anyway, 110, you cast it to char, A. Everything is A because this max file is, they're all A's. Does that make sense? So the take-home message is that pointer arithmetic, you have to be very sure what you are doing with pointers. The second thing is that you have to be very sure what this address contains, what data structures. It just contains regular data, then you can cast it to char. If it contains the addresses, you can cast it to int. If it contains the direct, cast it to direct. If it contains inode, cast it to dynode. So, I mean, this whole project is, it's a lot of thought processes. I mean, it's very easy to make mistakes. It's mistake prone, and so you have to be very careful. Okay, so I think I've done with the first part. Let's take a break, and if you have questions, you can ask. And for like 15 minutes, and then we'll go back to the second part. Okay. Go ahead.
How did you get your sample to compile? Because like you were referencing structs that were contained within XPs. No, they were contained within Makefile. Can you open up your
Yeah.
checker file?
So yeah, I was running checker. So checker.c is a regular Linux C file, right?
Okay.
And
Oh,
it
you said-
reads the file system image here.
Can you just scroll up
What's
all the
your
way? I think when I
includes?
was looking at it, I just saw crap. I didn't see. Oh, you can open it again. They're just header files that I was missing.
Oh, okay.
FS
And I was
H.
trying to see that. Okay.
Oh,
so you're,
yeah.
You're referencing types and
Exactly.
okay,
Okay, you can do the include here, or you can direct copy.
sure.
You can directly copy because include exactly the same with copying the things. You can do either way. Yeah. Any more questions? I don't want to like pause this the video recording, so let's just directly take a break and be back in 13 minutes.
Are you skipping heartbeat?
I gotta go.
I'm just
Basketball game.
Good.
I would stay. Also, I tend to enjoy just watching these things on like times 2 speed on YouTube. Or 1.5, depending on how complicated it is.
How do you feel about
A little back in, feels like a million years ago, but like,
No, it's just
3
great.
or 4.
So I'm still trying to figure out like where the FS directory is and like how that gets made. So I was.
I totally just.
That's fine. Well,
Do you have a preference on which part to do it?
so I pulled outside and ran this to the part.
No.
So I pulled this over. And then when I felt like when I make it, it doesn't create my fast direct. So like I'm just.
It's in tools.
Right, but I thought it was supposed to like happen automatically. So it's just everybody was saying is that like you know yeah, just do it from the machine. Just alright, so alright.
I think it's because.
So I mean, granted, this is not the first one.
Right.
Like, I mean, I'm recommending that for property.
You don't need make It's company for.
I mean, and I see where like we make a bus
Yes.
here, like you see that really goes. So I mean, this is the content we're supposed to be using for property, so maybe this just doesn't.
And you can go. You can see the
I wasn't thinking.
Yeah, it
That's
has
the for this one at least.
compiled it.
Where is it? Do I need to?
No.
And that there's so many different. So they open up so let's do these tests. I see once we get like one of those.
No, I don't think so. Yeah, I think this is just.
This won't change.
We don't always need to type make and then fast. I would just say
that makes sense.
Right, which is what I did. So I was like small.
So you
Try to
said when
take
you grab
one
it
or the
from
other.
I just- yeah.
that's
One and
compiled.
and then you have
I mean,
to
it's
finish the other part. So I'm just trying to figure out what makes most sense.
Yeah,
I'm learning a lot.
yeah, I think this hour I've
I think that's what's happened is I picked ones that have like a higher barrier to entry. So it doesn't save you time because you still have
So
to
we
use
just try to directly
Oh.
copy.
Alright, which
Yeah,
way?
using this
How do you?
copy dash R and then yeah.
They're the ones that really just starting.
Is this the source or the destination?
Source to destination. To
Yeah, good.
TA.
Put the source or just put it?
Dot, you can put a dot in the direct, yeah.
Either way, you know, and then we're going to be hyphen
There.
Would you mind just pulling open your checker real quick?
Sure.
I just there's another question about the reference.
Mhm. Yeah, I think there are a lot of includes for mmap, like the mman.h, for instance.
Yeah, what's that?
If you,
Use that.
I'm not sure if it's necessary, but like you can try to take mmap. Yeah, it needs the you need to include this guy for
Okay.
a map. And the unit standard and the function control f control is for like the system calls.
Mhm.
Yeah, like read, open, and types is also for open because you have the O mode type. And this types.h is for the xv6
Right.
defined.
Yep.
Yeah, you can just copy that. But, okay, let's just get started. I think the second part is I think it should be shorter. And yeah, I should have told you guys for part A and part B. In terms of coding, part A is more heavy. I mean, you have to like care about a lot of like edge cases for part A. But for part B, as long as you understand the whole workflow for like system call of write and read, I think it should be very straightforward and you don't need to modify too much in xv6. So for this whole project, yeah, I think you will spend, I mean, in terms of ratio, maybe 4 to 6. Oh, sorry, 6 to 4 in terms of A to B, basically. Okay, so like more times in part A. So the discussion for part B is, I think it should be shorter. So what part B does, and I'm not sure, in case you haven't walked through this guy yet, it's for like an optimization for xv6. So again, let's go back to what we have here. The regular file. So we have an indirect pointer here, right? And it points a bunch of more addresses so that we can have more data stored here. But what if we have a small file? Like we only need several data block, like only 2 or 3 data block. And for x86, we still have this indirect pointer, right? And for this optimization, we want to say for smaller file, probably we don't want this indirect pointer. We just treat it as a regular pointer, so that it holds another data until it grows large enough such that 13 blocks can no longer hold the entire file. And at that time, we'll expand this, use this, the last address as an indirect pointer to become the regular 2-level pointer, basically. So this is the simple idea, right? For smaller file, we don't use indirect pointer. We treat it as a normal file, a normal address. But for larger file, as file grows, we'll just go back to the original layout. That's basically the idea for this project. So the idea is very simple. And how to do that, and how to approach this. So yeah, here is a conceptual or another visualization. See, so this is a list of inodes, and this is particular one inode. It stores a bunch of addresses, right? In x86 case, we have 12 addresses to hold the data, and the last one holds the indirect pointers. And now, if the file is very small, smaller than 13 blocks, then the last one is no longer an indirect pointer. Instead, it's a regular pointer as the previous 12. So this is another visualization here. So we will just use GDB again to go through the entire write system call for this demo, where we will encounter multiple key methods, and we need to understand, and then we'll have an idea of how to approach this project. Okay, so I have another user program in x86. I wrote it beforehand. It's a very simple user program. Okay, this is now a user program of x86. It's no longer a Linux C code. Okay, so what it does, it creates a buffer, malloc some memory, which is the B size of the block size here. Okay, so the buffer holds some 1 block size memory. And now I open a file called testout.txt, set it as write only because I want to write something to it. And if it does not exist, I will create it. Okay, this is just a regular open system call in x86. And now I loop for like 14 iterations. Why do I do 14 times? Because each iteration I want to write 1 block. Okay, and if I write 14 blocks, what I will end up with? The first 12 blocks are written as normal, right? But from the 13th block, because in x86, the original x86, we don't want to write the 13th block here. Instead, this 13th block will serve as a new address pointing to a chunk of memory, another block where each of these integers stored in this block will point to the new data block. So 1, 2, 3, 4, all the way to 12, and the 13th block will be here, and 14, 15, etc. Now, because this test only up to 14, so 13 is here and 14 is here. This green one, this dark green one, does not hold the 13th block. Instead, it holds an indirect pointer, right? Points to this guy. So let's just walk through this. Here it's just populate this buffer with different letters. So for first iteration, it's just A. Second iteration is B. This is just because if A plus an integer, then it's doing ASCII conversion, right? So A plus 0 is A plus 1 is B, so on and so forth. After I populate the buffer, I'll just write this buffer, right, which is just one block size. And also I check if the return value is not what I write. So if I write n bytes, if I didn't get n bytes, then system call must fail. I want to make sure it doesn't fail. If it fails, it tells me. Okay, and that's it. It's just a very simple. So it just we just have basically two file system call relate here. One is the open, the other is write. I'll just set breakpoints at write to see what's going on here. Okay. Okay, so let's try to open two terminals. Okay, everything's ready. Sorry. GDB. Okay, this one, GDB. Let's continue first. The reason why I didn't set breakpoint directly here is because if I set like write, then this printing out is also calling write. And then I'll break so many times here, so I don't want to break it here. And now I just want to break at syswrite. Now I continue. Sorry. The user program is called write. Okay. Okay. Now we are in syswrite. This is just normal argument checking. You must be very familiar with. And after this arg thing, we get a bunch of the parameters, right? The f, the p, the n, which is required for the system call, which is required for the file write. We can take a look at n. So it's 512, which is the number of bytes. Okay, that makes sense. What is p? This p is the pointer pointing to the strings we want to write, right? The contains of what we're gonna write. So it's a bunch of a's. That makes sense. And the first one is actually the file descriptor, and it's corresponding to a struct file. If you dereference it, you'll see it's got a bunch of type. And this is the offset. Why do we need to maintain the offset is because each time you call system call of write or read, you'll shift the offset, right? So that's where you store here. You'll write different things. You'll just continue writing or reading. And here, the IP is actually the data structure of the inode. You can IP, yeah, it's still struct inode. So note that this is inode, but for this guy, it's dynode. It's slightly different. I mean, the structure looks exactly the same. The only difference is the purpose. So for dynode, it's for on-disk inode structure. For inode, I think it's for like in-memory, the inode structure. So there are like two copies in x86. So basically, for part A, you can always use dynode. For part B, you can use inode. So that's the, I think you can just treat it That's the only difference. Okay. So if I dereference this inode, you can see this is the inode of the particular file I opened, right? Oh, yeah, because I think I didn't make clean, so that's why I think in the file system it's already there. So sorry, let me do that again. Sorry, yeah, because if you do ls, yeah, it's already there. So let's just make clean. Sorry about that. Okay, continue and break at right. Oh yes, exactly. Sorry. Yeah, because we don't have write method in kernel. Okay. Okay, let's write. Okay, everything's good. Now let's print the f IP, which is the inode here. We opened just now and try to dereference it. You'll see the addresses are all 0, which means this is an empty file. You just opened it, right? You didn't write anything to it yet. This is just a inode. So when does this inode create? When does it get created? Or when was it created? I think I need a third. I need a third term. Base. So let's take a look at our user program called write.c. We were setting breakpoint at syswrite must be here, right? And when we look at it in write, we have seen that this inode has already been created. So my question was, when was it created? Exactly. When you open it, you created this inode. For the sake of time saving, I will not break it into here, but you can do that after class. But like, it makes sense, right? When you open a file and it doesn't create, it's not existing, then you try to create it. Then you create the inode, right? This is completely makes sense. So that's why when we write it, the inode is already there. Okay. Now let's try to step into file write. Okay, now we're in file write, and you can see the argument gets parsed as f, address, and n, right? F is the F data structure. I think it's called file. So F is a struct called file, and F has a field called inode, and address is actually the starting address of the contents you're writing, right? It stores on the heap, right? Because you malloced it, right? So only 2 zeros, right? Not 3 zeros. 0 is stack, but here's 2 zeros. Okay, so it's on the heap. And n is number of bytes you want to write, which is 1 block, 512. Okay, so far so good. Okay, it's writable. It's not a pipe. It's an inode. Okay, then because we're trying to modify this inode, right? We're making a lock to that to protect it. Okay, now we enter another key method, which is called write I. Okay, we pass the inode, we pass the address, which is the content we are writing, and this is again the offset of where we have written, right? Because this is the first write system call we called, so it starts from 0. Okay, see, so off is 0. And n is 512. Everything makes sense. Now let's step into write I. So what does write I do? Again, does a bunch of checkings to make sure it does not go out of the bounds, does not go out of the max file, right? Okay, now we enter a for loop. Each loop, we have a sector number. So in x86, the sector number is equivalent to the block number. Okay, so every time you see a sector number, it's always indicating the block number. Block 29 or block 44. Okay, so this number is obtained by another method called bmap. Okay, so let's again step into bmap. This is the key method. So in bmap, it gets 2 arguments. One is the inode, okay? The other is the offset divided by b size. So offset is 0. So why do we divide this offset by block size? Any idea? Sorry? Yeah, this is a integer division. Yeah, exactly. So because this is off is still 0, so probably it's not very obvious. So let's say suppose off is 1000. So we're writing the 1000th byte, and we have to first determine how many blocks we have written, right? So that's why we divide it by the block size. So 1000 divided by 512 is 1. So we start from the we don't want to rewrite the zeros block, right? It's already written. 1000 is residing in the index 1 block. So that's why we pass this number into bmap. And bmap essentially, as the name indicates, it maps this inode and its corresponding offset to the sector number, which is the real block number. We want to locate which sector or which block is it. So that's what bmap does. Okay, let's see. So bn is the argument, which is corresponding to off divided by b size, which is 0 here. Okay, everything's fine. And n direct is actually 12, right? If we can still remember. I think I didn't have screenshot here. But n direct means the number of direct entries, which is 12, okay? So bn is smaller than 12. Now we are trying to get the address of this entry, right? So bn is corresponding to which entry of this address of the regular file. So we can print IP's address. So now everything is 0. So like address is also 0. So this if statement holds. So if it's 0, which means it's not allocated, right? Or it's not written, then what do? We basically allocate this block. Okay, and I will not step into balloc, but what it does is in high level, it's just create or register a new block and return this block address or sector number. So this is what block means. balloc means, and so you can see from the semantics of balloc, when it creates a new block, register a new block, return its corresponding address, what will it do internally? What else will it do? We always modify the bitmap, right? Because I'm now allocating a new block, so the corresponding bitmap will be also updated from 0 to 1. So that's all done in balloc. Okay, after we allocated a new block, now we will return an address. So let's see what this address is. Okay, so it's this number, 434. So it's much greater than like 29 or 44. The reason is that we have already have those list of files, right? Like the README, all the executables like link or ls, cat, echo. They all taken up these previous addresses. And the lowest or the new address I got is 434.
So the address is a block number though, it's not like a memory.
No, it's not a memory. It's just a block number or sector number. So that you can calculate it from using the pointer arithmetic, from part A, Okay, so you get this new address. Now, that's it. You will return from bmap. So after I return from bmap, now I got a sector number, right, from right eye. So in right eye, you call bmap, and we return the sector number, which is the 434. And the sector number is not 0, right? Which means it successfully finds the block. Now what? Now we obtained the new block. I obtained the new block number. Then I'm trying to write some. Not yet. Not yet. What do? We first read this block. Why do we do that? I think BP is the buffer. After we read, let's see. So this is oh, okay. I know what it does. So before we write something to this new block, why do we need to read it first? So potentially we will rewrite or overwrite a certain block, right? So we have to read it first to make sure that this block is empty. The data is all 0, is empty. And then, let's see. Okay, so I think, I'm not sure. I think this BREAD, or you can read it as bread, is just for returning a buffer, which is called BP. And BP here has a field called data. And we want to, because you can see here, man move is basically just copy the source to the data in BP, right, in the buffer. You can take a look at what source is. Yeah, source is what you are writing, basically. You're just copying or moving, not moving, just copy the source to the buffer, basically. Okay. And after you man move, you can see that now in BP's data is all A. Now A's are populated in BP, in the buffer. And after we populate the buffer, finally we will write this buffer to the disk, basically. So the process is we will not directly write things to the disk. Before writing that, we'll store it into the buffer. That's the normal I/O. What I/O does, right? We'll always have a buffer so that we'll save some time. So finally, we use bwrite to copy the data from the buffer to the disk. I will not go into bwrite here for save time. now B release is like a lock, because you can still remember, right? Previously we have to lock the inode, so we will release the lock responder. And now we enter another iteration. Let's see, what is total now? I think total is already 512, and n is also 512, so this is no longer hold, so we break out of the for loop. And then we record the size of the file in the, which is 512, right? And finally we return. So this is what the whole system call for the write does. So if we take a look at IP now, oh no, I have already been out of scope. So to summarize, yeah, there are several key methods we have to pay attention to. The first one is write I, right? It's in kernel sysfile.c. In write I, we call bmap. The only purpose, not only, the purpose for bmap is essentially just check if a specific address is 0 or not. If it's 0, then it means it's unallocated, and we try to allocate a new block, and then finally return that sector number or block address, so that we can obtain a new buffer from bread, and then populate the buffer with the source, which is the data we're going to write, and finally write this data to the disk, write the buffer content to the disk. So the key thing is in the bmap. Why it's important for this project? Because now for smaller file, we don't want to use these indirect addresses, right? So if we take a closer look at bmap, why do we have here? So this is a user program. So let's take a look at kernel bmap. So not bmap, it's where is it? fs.c, right? Yeah, fs.c. So this is what bmap does. And essentially, we were just at here, right? Because bn is just now we have only 0, because we're writing the 0 from 0 to 512 bytes. So it's still at the very first address. We're just writing the very first address, right? So we're only reaching here. But as we write more and more data, this bn will grow all the way to 12, right? And if it's 12, then this does not hold. Then we should go to this case, where we'll consider the number of indirect addresses, which is 112.8. Right? Sorry, 12.8 or 128. So it's just when we reach the indirect addresses, the number of indirect addresses are 128. And then we will consider about the indirect addresses. This is for this case. Now let's take a look at, let's just try to break here to see what happens if the files grow so large that we need to use the indirect addresses. So I think we can just break at specific line, which is 343. So let's see. Let's continue. Yeah, I set up so many sysfile break. So let's just quit and break at fs.c343. Okay, let's. Oh, yeah, I know what's happening here because at the very beginning we are also writing the README, which is also a very large file, so it already hit there. Oh. Continue. Yeah, there are a lot of large files. But... Okay, here we go. Now let's call write this user program. Okay, now this is we are writing our own file, right? Which is large enough and it hits this case. And when we print out the IP here, okay, so inum, okay, this guy has got an I number of 21. It's a regular file with a type of 2 that makes sense, consistent, and size is this many. And look at it. Look, the addresses are starting from 434, right? This is exactly the very first address we allocated. Now, after we've written, sorry, I think I messed up again because I just now I run write here, but I didn't make clean, so it's already there. Sorry, I should redone. Make clean. We'll break, continue first, and then break C and break at fs.c 343. Okay, right here. Okay, here we go. Now let's try to print IP. See, so we have already written the first 12 blocks, which are all direct blocks, right? That makes sense. Now we are hitting here because we have exceeded 12 blocks. So we have to consider creating the indirect blocks. So that's why we enter here. So let's see. So for this line, the address is 0, right? Which means we have to, which is corresponding here, right? And then we have to create a new block using the balloc to store at here, right? This is 12. So IP address 12 is corresponding to this entry. We want to first create a new block, store here, but this block is no longer holding the regular data. Instead, it will hold this guy, right? It's not holding the regular data anymore. It's holding a bunch of addresses. So now we get address to be 446, right? Everything is good. Now we have 446, but now 446 no longer stores the data. Instead, it stores the indirect address. How to do that? We will, what? I don't know what is happening here. Yeah. Okay. So we will first cast this data in a buffer to an integer, right? The reason is that these stores integers, right? And then we'll check this corresponding entry is not 0. If it's 0, then we'll try to allocate a new address for this guy, right? Pointing to a new data. So you can print A now. A's first entry, for instance, start 5. So you can see this is the first blocks we created. This is the second, and this corresponds to the 13th blocks, right? This is the 14th block, and 446 points to this block, basically. If you go to print IP's address, yeah, 446. And you can also print BP's data. Doesn't make much sense until you cast it to int. And then you do, first entry at 10. Yeah, this is what we stored into the buffer, and then we stored into the buffer. We update the corresponding address, and then we write the buffer to the disk, or update the images, basically. So this is the case where we have like a big file, and we want to extend the last block so that it's an indirect block, right? And then we create a array that's got 128 addresses or entries, and then we populate these with the new allocated blocks. Okay. So for this project, for part B, you'll take a very close look at the B map, basically, to see how to modify it correspondingly. So the idea, again, is that when we hit this guy, the 13th block, if the file is just equal or smaller than 13 blocks, you'll do the regular, even for the last block, it's still a regular file, regular block. It's not containing these new addresses. But once it grows up to 14 blocks, then because there are no room for it, right? Then you have to restore this 446 or restore this the last block back to the original indirect block, and then move the 13th block to here and the new 14th block here. Does that make sense? I can draw a diagram here to be more specific. So the old version is you got 12 blocks, right? And this guy is the 13th. For the old one, it's always containing the indirect addresses, right? And for the new one you are going to implement is when the file is very small, when file size is greater or equal to 13 times the block size. Because if it's just 13, then you can always fill in every block here, even for the last one. Then this one is also a normal. It also stores the data. However, when this file continue growing, like above this guy, then this does not change. And this the last block will be restored to this indirect address holding a bunch of, sorry about this case, integers, and then we will move this data. The first entry will point back to this data, and another entry point to the new data. Let me just redraw it. It looks very messy. Okay, this is the new one. Old one's fine. Okay, for the new one, that is small, smaller than 13 blocks. For the last one, just treat it as a normal group. Okay, now if it grows, these are still data. We can just reduce. Okay. Exactly the same thing. Okay, now here it's no longer pointing to the data. Instead, you should allocate a new block. But in this block, it does not contain data. Instead, it contains 128 addresses, right? Because 128 is 512 divided by 4, right? 4 bytes integer. And the very first address will point back to the original data you have, right?
That stays in its original block.
Right. And the second block is the block you want to create. And the rest are still empty. And if you have more blocks, you just go out. Does that make sense? This is, and because this is all corresponding to the mapping, like how to get the sector number or the block number. So these all happens in VMAP. So you definitely have to look at VMAP and try to modify it.
So when you're doing like one write operation and you're in VMAP, if you know from the start of it that the file size is large enough, it's not necessarily like within that one operation to start off in the old method and then switch, right? Or is it?
If you take a look at, yeah, that's a good question. If you take a look at the detailed implementation of write, I think it enters a loop that's, you can take a look at here. Oops. 8 o'clock, okay. Yeah, let me take a look at, I think it's 5, 6, 5. No, I think it's there. Okay, sysfile.c. Right. Okay, so this is the right eye, right? So you can see this is a for loop. in each loop, it looks for a new sector number based on the offset. So I think this is doing, depending on how many bytes you want to write at once, right? If you are writing like block by block, then definitely the layout will change. But if you are writing a very huge chunk of memory at a time at once, then I'm assuming there is no issue of you don't need to consider about the small file optimization at all. Because you can see here, yeah, every iteration increments by m. And yeah, there's a complicated m calculation here. For each iteration m is changing. I'm not quite sure why we're doing this, but I think probably because it makes sure that it's always block aligned. So n is always the byte you want to write, right? And total is yeah, I need to print out what total is. I think total is always smaller than n. Okay, total. I think total. Okay, total is the number of bytes written so far. Okay, n minus total is like how many bytes remaining, right? Versus 1 byte, the block size minus I think this is to make sure that you are not exceeding 1 block size and not exceeding the total number of bytes you want to write. So, yeah. So what if, so say you are writing like 500 bytes for the first time, and after this your off is at 500, right? And then you are trying to write 100. Then for this for loop, you will first write 12 bytes to reach the B size, and then write the remaining 88 bytes. So I think this is just to make sure that you are every time you are block aligned, basically, like page aligned.
What are we in here, right eye?
Sorry?
What are we in here? What is showing?
Write eye is called by file write.
What function is that?
But the thing is,
And
it's
that's
right, like
Yeah,
the
this is
file
red
is
eye.
already-
So yeah, I think probably my statement just now was incorrect. I said if you are writing like, so what if you are writing like
Seems like when you
2000,
block 13,
I think you will loop, this iteration is at most 1 block size. So you have to do like 2,000, at least 2,000 divided by B size, this many times. And each time it looks for a new sector number, right? So, and since it looks for a sector number, it will call bmap, and bmap will do like everything in this stuff. So I think no matter how many bytes you're writing or how many times you're writing, it's always like block by block.
Actually, it says right here in the overview that we
doing everything as a small type, and then type related needs to enlarge and reissue.
So what's a TDAG as a device?
Yeah, I forgot to mention, we don't want, this optimization is just like a completely different type of file. It's not, for the regular file, it's still maintaining the original version. We're just creating a basically new file type called tsmart, yeah. To,
Oh, there's a flag that
yeah, there's a flag you can control.
that you call it. That so I guess you could start off creating a new file, but like when you call,
You don't have to shrink.
Right.
you send this OSmart flag to it.
So simultaneously, you should be able to have normal files or smart files.
Right.
created, and then the smart files grow when they hit certain size.
Any more questions? I think I'm done with this part.